Ever try to imagine a world, like, without computers? It seems kind of crazy now, but that's where we're going today. Get ready for a deep dive into Alan Turing's 1936 paper on computable numbers. We're talking like the bedrock of theoretical computer science before computers existed.
Wild, right.
Totally. And joining me is our expert to help unpack Turing's work. We've got insights from the Stanford Encyclopedia of Philosophy and even a 2024 paper that builds on Turing's ideas. What blows my mind is that Turing wasn't like just doing math problems. He was trying to define what it even means to compute something.
It's true. His work was, groundbreaking. It's like imagine writing the rule book for a game that hasn't been invented yet. A game about what's possible with a set of instructions, a program.
Oh, I see what you mean.
Turing was doing just that. And he started with numbers because, well, at their core, that's what computers work with.
It's like he was like a tech prophet or something, seeing the potential of computers before anyone else. So where'd he land? What makes a number computable in Turing's world?
So, initially, he had this deceptively simple idea. He figured if a machine could just, churn out the decimal representation of a number digit by digit, then bam, computable.
Okay, yeah, that makes sense. What could be the problem with that?
Well, that's where things get kind of interesting. Turing, genius that he was, quickly realized there's a flaw in that thinking. It involved something as basic as, believe it or not, multiplication.
Multiplication. You mean computers wouldn't be able to multiply?
No, not that. It's a bit more nuanced. The problem comes up when you try to multiply a printable number 1, whose digits a machine can spit out by a simple factor, like 3.
Okay, I'm going to need an example. What kind of number would cause this, like 3x problem?
Okay, let's take the square root of 2. We know we can calculate that, at least to a certain accuracy, right? Theoretically, we could keep calculating digits forever.
Right, keep going.
But here's the thing. Turing realized that even if a machine could print out the digits of the square root of 2, there's no guarantee it could do the same for 3 times the square root of 2.
Whoa, okay, now that is wild. Why does simply multiplying by 3 throw a wrench in things?
It boils down to this. A number's decimal representation, it doesn't necessarily tell you everything about that number in a way that a machine can use. It's like having a map with landmarks but no roads. You can see where things are, but you don't know how to get there. Turing was grappling with how to represent numbers in a way that a theoretical machine could actually work with, not just display.
So his initial definition, it was kind of like a car without an engine. It looked right, but couldn't actually go anywhere. He needed a more, I don't know, a more precise way to define computability, something that wouldn't fall apart with some basic math.
Exactly. And that's where these things called Cauchy sequences come in.
Ah, yes, Cauchy sequences.
They provide a much more, how should I say, robust way to define and approach a number, and they hold up even when you start multiplying.
Cauchy sequences. Those are ringing a faint bell from college math maybe. Our listeners could use a little refresher too.
Absolutely. Picture a sequence of numbers that keep getting closer and closer to a target value, like, say, 1, then 1.4, then 1.4, 1.414, and so on, all homing in on the square root of 2.
Okay, I vaguely remember this now.
A Cauchy sequence means that no matter how tiny a distance you choose, you'll eventually reach a point where all the numbers in that sequence are closer to each other than that tiny distance.
So instead of just looking at a number's decimal expansion, we're looking at a way to, like, approach that number with ever-increasing precision. Did this new approach solve that multiplication issue?
Exactly. With this new definition, the 3x problem just vanishes. If a machine can generate a Cauchy sequence for a number, it can also generate one for 3 times that number. It's just more elegant, more powerful way to think about computability.
Cauchy sequences to the rescue. Okay, so we've got this more robust definition. But something tells me this is just the tip of the iceberg. There's a but coming, isn't there?
Oh, there's definitely a but. And it leads us to a pretty mind-bending concept. It seems natural to think that if a machine can print out the digits of a number, it's got to be computable, right?
Yeah, that seems like a given. If you can generate the digits, it should be computable by, like, definition. What's the but here?
The but, and this is where it gets really wild, is that there are numbers out there that are computable. We can define them with a Cauchy sequence, but no algorithm can actually print out all their digits.
Hold on, wait, really? How is that even possible? Are we talking about, like, numbers that theoretically exist but we could never actually see?
You got it. It all comes down to the information packed into those digits. Okay, imagine a number, but it's represented in binary, so just ones and zeros.
Okay, got it.
This number, it's computable. We can define it with a Cauchy sequence, but the pattern of its digits, if we could see the whole thing. It would actually solve a problem that we know is unsolvable, like mathematically impossible.
Now you're speaking my language. What problem are we talking about?
The halting problem.
The halting problem, right. Remind me what that is again. It's been a while.
So imagine you've got a computer program, and you're going to run it. The halting problem asks, can you write another program that can look at that first program and tell you for sure will it eventually stop, or is it going to run forever in a loop?
So you're trying to predict if a program will, like, get stuck or if it'll actually finish running.
Exactly. And what Turing and other mathematicians figured out is that there's no universal algorithm, no single program that can solve the halting problem for all programs. It's just fundamentally not possible.
So this binary number we're talking about, it's got the answer to the halting problem baked into its digits.
It's wild, right?
That's kind of amazing and terrifying.
It's both. It's like those digits are a secret code, and inside that code is the answer to a question we can't always solve. So even though we can, like, define this number mathematically, we could never create an algorithm that would spit out its digits in a predictable way. There's no pattern a machine could follow.
So it's like having a map that shows where the treasure is, but there are no roads or paths to get there. You know it's there, but you can't actually reach it.
Perfect analogy. And that's the core of what Turing was digging into, the fundamental limits of computation. Even if a number is computable, the information in those digits might be totally off limits to us.
Okay, so we've got computable numbers, printable numbers, and now this whole other category of numbers that are computable but not printable. My brain's doing backflips trying to keep up.
Yeah, it's a lot. But the key takeaway, Turing wasn't just like categorizing numbers. He was trying to understand computation at its deepest level. What can be computed, and maybe even more importantly, what can't be computed, even with like these theoretical, infinitely powerful machines.
It's like he was drawing the boundaries of a whole new world, one that, honestly, we're still trying to explore. But you mentioned earlier that Turing applied these same ideas to functions as well. What are computable functions? And how do they fit into this big picture? Computable functions. Okay, it sounds like we're going even deeper down the rabbit hole here. Can you give us an example of a function and, like, why it would or wouldn't be considered computable?
Sure. Let's stick with that halting problem since it's such a, clear example of how tricky this whole computability thing can be. Imagine a function. It takes a computer program as input, looks it over, and then spits out a 1 if that program halts, a 0 if it runs forever. Sounds simple enough, right? Like a computer can handle that.
Yeah, on the surface, it seems like you just, like, check if the program eventually hits a stopping point. Why wouldn't that be computable?
Because, and this might sound familiar, there's just no algorithm out there that can do that for every single program. We're right back to the halting problem. You could have a program that looks totally straightforward, but it ends up in this infinite loop. And there's no way to predict that without actually running the program. So this function we've described, one that seems like it should be simple, just giving us a 1 or a 0, it's actually uncomputable.
Wow. Okay. So even though we can describe the function, and it seems like it should have a clear answer, the task itself is impossible to program in a way that would work every single time.
You got it. And that's, I think, what makes Turing's work so important, so groundbreaking, this halting problem. It keeps popping up, especially when we start talking about the limits of what computers can do, even theoretically. It's a fundamental roadblock. It tells us there are some tasks that even the most powerful computers we can imagine could never solve perfectly every time.
That's kind of a humbling thought. So it's not even about, like, building a better computer. It's about the nature of some problems that makes them unsolvable, at least in a general way.
Exactly. Turing opened up this whole new field of study, what's computable, and more importantly, what's not. And it's not just theoretical, it has implications for everything. We're talking cryptography, software development, even our understanding of the universe.
Wow. So what does all this mean for, for us? Living in a world where computers seem to be able to do more and more every day, are there, like, everyday examples of this computability problem that we might run into?
It's a great question. And it gets to why Turing's work is still so relevant today. Think about something like AI, artificial intelligence. We're making crazy progress with AI. Systems that can learn, solve problems, even be creative. But Turing reminds us there will always be limits to what these systems can do.
You mean, like, some problems are just too complex, too much going on for any algorithm, no matter how fancy, to really crack?
Exactly. Makes you think twice about those big questions, right? Like,
Yeah.
could we ever create an AI that truly understands human emotions
Right.
or predicts the future perfectly? Turing's work suggests Maybe not. Maybe those problems are just inherently uncomputable.
That's that's a pretty profound thought to wrap up on. We've gone from this theoretical world of computable numbers to like the very limits of what we can know.
Yeah.
And it all goes back to Alan Turing.
It's pretty amazing. Even decades later, his work is still shaping how we think about technology, knowledge, the whole universe.
It really makes you wonder what Turing would think of how far we've come and where his work might take us next. Listeners, if this deep dive piqued your interest, don't stop now. Dive into the world of computable numbers, the halting problem, all these mind-bending ideas. It's a journey that'll make you question everything, and that's what makes it so fascinating. Until next time, keep those brains buzzing. We'll see you in the next deep dive.